Hi, welcome to the live session 5 with the Quantum Topology Part 2 admin course. This is Shovik, one of the tier for this course. Before starting, let me know. Who is Mustab? Okay. So before starting, can you please let me know whether I'm audible and is the screen visible to you properly? Please let me know. Mustab, please let me know whether I'm audible and is the screen visible to you properly. Okay, it seems. Is there any kind of internet issue? Well, let me.
Yes, you are audible.
And can you please confirm whether is the screen visible to you?
Yes, screen is
Oh,
also visible.
okay, thank you, Mr. for your confirmation. So before starting, before starting further, please let me know if you are doing any question or query from the previous sessions.
No, no, you can
Okay,
continue.
okay, thank you. Okay, in the meantime, if you have any doubt, please stop and ask me. Okay, so what is that? Okay, so in that case, so 1 minute. Hmm. Okay, so so today we shall start with um, today we shall start with assignment, a subjective assignment 3. Okay. Okay, so that 1 minute there is okay, so this subjective assignment 3. Hold on a moment, please. Okay, so subjective assignment. So today we shall start with the subjective assignment 3. Okay, so the first problem is that okay, so first let me write on the questions and please take your time to solve by yourself first. If you're unable to solve, I shall do this for you. But of course, first you should try. Okay. So first question is show that every closed subspace of a paracompact space is paracompact. Show that every closed subspace of paracompact space is paracompact. Okay. Please take your time, think about it. So first, you should recall the definition of paracompactness. Okay. So think about. I mean, of course, I'm not going to tell the definition. So you all know the definition of compactness is that every open cover has a count. Every open cover has a finite subcover, right? And linear of millions means every open cover has a countable subcover, right? So now from this, just recall the definition of paracompactness and try to solve this problem by yourself first. Okay. Basically, in compactness space, you have in case of compactness, you have done the same thing. There's a closed subspace of compactness is compact. Okay. So use the same definition and try to do it by yourself. Okay, I mean use the same technique. So in the compact case, what you have done, suppose you have given a closed set and you need to show subspace the compact. So what you have done, you have considered open cover and show that that open cover union x minus f is an open cover for the whole space x. Okay, so that was a trick. Okay, so take your time and think about it and let me know. Okay, first think for a few moments, then I shall tell how to approach this problem. Okay, please take your time, let me know. So basically, the solution is nothing but basically just hint is that replicate the proof from compactness situation. So if you replicate the compactness situation, you shall understand um, the same. Uh, I mean, basically just try to replicate it by yourself. Okay, there is nothing to explain more. I've already explained the many things. Try to figure it by yourself. Okay. In the meantime, okay. So in the meantime, it turns out that few of you has not submitted the assignments. So it's a request to submit the assignment as much as possible. Okay. If you're unable to understand something, please try to utilize these live sessions because this live session is actually meant to uh, understand clear orders. Also, after due date of each assignment, you can ask those assignments in order to clear your doubts. Okay, because understand doubt is very clear in topology. Otherwise, in exam also that will create a very problematic situation. Okay, I do understand. I hope you understand the situation. Okay, so please try to solve it by yourself. Hmm. So, uh, so wait for a few minutes. I shall wait for a few minutes, or else if I don't get an answer, I shall explain the solution to you. Let's take your time and let me know if you are able to get some kind of idea or solution. Okay, please take your time. Okay, so it seems there is no answer from students. Okay, so let me explain why. Okay, so so I'm writing the solution. If you have any doubt, any questions, please unmute yourself. Ask me. Okay, because if you don't ask, then there is no point of taking the session. So please try to utilize this patience as much as you can. I hope you understand. Okay, so the solution is let sorry A be a closed subset of a paracompact space X, okay, and let U alpha be an open cover for A, okay. Then second bracket U alpha intersection A complement is an open cover for X, okay, and paracompactness of X, using paracompactness of X, there exists locally finite open refinement V beta of U alpha union A complement. So what does this tell? This tells that the collection V beta intersection A, this collection is a locally finite. This collection is a locally finite open refinement of UR. So this is the argument. So the argument goes as follows. So the argument goes as follows. Okay. Let A be a closed house of paracompact space X and U alpha be an open cover of A. Okay. Let U alpha union A complement is an open cover for X. Now, using the paracompactness of X, there exists and locally okay, there exists locally finite refinement V beta of U alpha intersection A complement. So this V beta intersection is a locally finite open refinement of U alpha. So that is the thing, okay. So basically what we have done, we basically replicate the technique for the same if the given f is compact, right? The same thing we have replicated. So I hope you understand the argument. Please take your time and let me know if you have any doubt or any question from this solution. Or else we can go to the next question, okay? Please take your time and let me know. Mm. Mm. So, uh, okay. So I hope this argument is clear to you. So now we shall go to next question. But before going to the next question, we have a following definition. The definition is that a topological space is said to be sigma compact if it can be if it can be written as a countable union of compacts. A topological set is simple compact if it can be written as countable union of compact set. Okay. So now the question is that show that a locally compact Lindelof space is sigma locally compact. Okay, so that is the question. So a locally compact Lindelof space is sigma locally compact. Sigma locally compact means what? Every point has a neighborhood which is locally compact. Okay, so that is the definition. Think about it, take your time and let me know. It is very, I mean, okay, it is, I'm not saying it is easy, but of course it is a bit easier. It is not that much difficult. Okay, take your time, let me know. So keep in mind definition is the sigma locally compact means the space can be written as countable union of locally countable compact set whose closure is also compact. Okay, that is what we mean by sigma locally compact. Okay, now think about it, take your time, let me know, and try to use the definitions. Okay, please take your time. I shall be back in a few moments. Oh. So in case if you are not sure how to start with, the point is that you start, I mean, go along with the definition. There is really nothing to do extra work for solving this problem. Try to use the definitions as much as you can. Okay. Of course, you need to use some kind of trick, but try to use the definitions first. Okay. Take your time and let me know. I'll still back with a few moments. Are you are you able to figure out how to start this problem? Any idea? Any guess? So there is one student, Mustaq. So Mustaq, can you please unmute yourself and let us know how to start with? Mustaq, can you please unmute yourself and let us know the how to start this problem with? Do you have any, I mean, any idea, any guess? Okay, so let me. Okay, so let me write down the solution. Okay, by local compactness of X. For all X belongs to X, but this is by definition. For all X belongs to, there exists an open set Ux such that X belongs to Ux and Ux closure is gone. Okay. Ux closure is compact. Okay. And by Lindelöfness, there exists Uxi that covers X. Hence, X is equal to union I is equal to 1 to infinity Uxi closure, and each Uxi is compact, which implies that X is sigma locally compact. Okay. So what I'm saying is the following. Basically, so local compactness of X tells that for all X belongs to X, there exists an open set Ux such that X belongs to Ux and Ux closure is compact. Okay. Well, in the Loveness, there exists a UXI that covers X. Hence, X is equal to union of UXI, and for each UXI, the compact implies the X is sigma locally compact. Okay, is the argument clear? So that is the full argument. Okay, so please take your time. Let me know. I shall be back in a few moments. Okay. Mm. Oh, so I hope this argument is clear to everybody. In case there is no doubt within the argument, you can ask me. Okay. Hmm. Okay. Okay. Sure. Let me. 1 minute. So let me go for the next question. Given an open covering U, one. Okay. So question is given an open covering U is equal to U alpha J of a paracompact space. Given an open covering U of a paracompact space, show that there exists a partition unity theta alpha, where alpha belongs to J and that is indexed by the same set J such that support of theta alpha subset of U alpha. Okay, so that is the question. So hold a moment. So basically, what does this question is telling? If we have a paracompact space and we have an open covering, which is house drop, then we are able to find a partition of unity such that whose support lies entirely on U alpha. Okay. The hint is that basically replicate the proof for the real case. Replicate the proof of real case. Okay. Take your time. Let me know. So replicate the proof for real case. Take your time. Let me know. I'll try the 2 minutes. So are you able to figure this out? Okay. In this not, so let me solve this for you. Okay. So given an open covering U, so we have the given open cover. Okay. Now since the space is paracompact plus Hausdorff, so given any open cover U, there always exists a partition of unity which is subordinate to U. And we're choosing a function rho from I to J, PR refinement. That is, we are choosing this as a support of eta I subset of U of rho I. And now defining theta alpha is equal to summation of the I. And now it is obvious or easy to check that this theta alpha is indeed a partition of unity on X. Okay, so that is the argument. Basically, we have given open covered U alpha, a paracompact Hausdorff space, and such that there is a partition of unity indeed for same J. So the argument goes as follows. So it is well known that for a paracompact Hausdorff space, we'll always have a partition of unity. Okay, so we are choosing a refined function rho I to J, so the support of eta I subset of U rho I, and we are defining theta alpha to be summation eta I rho I is equal to alpha. We have checked that theta alpha is indeed the partition of unity. So is the argument clear? Please let me know. Is the argument clear? Please let me know. So is the argument clear? Please let me know. So, so, not only that, basically, Additionally, we can say that support of theta alpha, this particular thing, can be read as union of support of eta I such that rho I is equal to alpha. Is closure. That is equal to union of support of eta I such that rho I is equal to alpha. This is subset of ui. Okay. So is this argument clear? Please let me know. Take your time. I shall back in 4 moments. Okay. So I hope this argument is clear to everybody. Now, so now let's move on to the next question, namely, this question particular asks that show that a space is sigma locally compact if and all if it is sigma compact and locally compact. So this tells what sigma locally compact is nothing new. Basically, it is a consequence of locally compact and sigma compact. Okay, basically that's the thing. Okay, so basically the hint is that try to use the definitions. Just play with the definition. That is my hint. Okay, take your time. Let me know. The problem is highly solvable. Okay, take your time. Let me know. Okay, in the meantime, there is something I want to show you. Okay, you please try. Let me go open the website. Okay, please try to solve the problem. There is some interesting website. Hmm. Hmm. What is that? So, uh, see, so there is a website. So this is a website you can see. The name of the website is Topology Atlas. Okay. So basically, it's a basically it's a famous University York source. So there you can find different things about topology. Okay, this is one website I want to share, and there is another website called this Topological Atlas. You can see. So just remember the website that is Topological Atlas. Okay. Mm. Same, there is an issue with the website. Let me topological topology atlas. God knows how this website is. Maybe there is issue with the website. Anyway, I cannot do anything for that. The point is there is some website which actually um, known as topological atlas. Okay, and that website is quite interesting. Why I'm saying this because what is that? That is actually quite interesting anyway because that particular website serves of many different purposes. Okay, so let me open it. God knows. So this website seems there are many. This website has some problem indeed, I guess. Okay, so leave it. I cannot do anything in that. There is so there are some website I can. Okay, apart from this, there are. Okay, anyway, the point is that there is some website for topology atlas. Keep it in mind. Whenever you're free, to just have a look around this website. Okay, this is very interesting, and you can ask many questions there. Okay, so that's why the topology atlas the site is very interesting. Okay? You should not forget about the site. Okay, now let's go back to our main question. Hmm. So anybody able to solve this question? Okay, please take your time. Let me know. I shall be back in a few moments. Okay, so okay, so the solution goes as follows. So there are two-part solution. First, I am doing the if part. First, I'm doing the if part. Okay, by sigma compactness of X, there exists an increasing sequence of compact sets Kn prime such that union 1 to infinity Kn prime is equal to X, and then by local compactness for each X belongs to X, there exists an open set U X such that X belongs to UX and UX closure compact. This is because of local compactness. Okay. Now we are constructing a sequence of open sets Vn inductively such that Vn closure is compact and Kn prime subset of Vn. And to get started, consider V0 to be empty set and suppose Vn minus 1 is already constructed. Now, since Kn prime subset of Vn minus 1 closure is compact, so there exist points x1, x2, xr such that Kn prime union Vn minus 1 closure subset of ux1 dot 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 un uxr. Okay, so this is nothing but v, and this tells what? Vn closure, that thing is equal to ux1 x closure dot 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 uxn closure. Okay, so and this is compact. Okay, and Kn prime subset of Vn. This implies what? This implies X subset of union of n Pn. Okay, are you understand? Are you following? So basically, 1 minute. Basically, what we are taking Vn closure is equal to Ux1 closure union Xn closure is compact. But Vn close subset of Vn. This implies X subset of Un closure. Okay. So the if part. So how this goes? Sigma compactness of X implies there is an increasing sequence of compact sets Kn prime such that union Kn prime is equal to X. The local compactness for each X belongs to there is an open set Ux such that X belongs to Ux and Un closure compact. So from this, what we are basically constructing a sequence of what? Of open sets Vn inductively such that Vn closure is compact and Vn closure subset of Vn. To get started, we start V0 is equal to empty set. Okay. Vn minus 1 is constructed already. Now we are choosing the points x1, x2, xs of Kn minus closure union Vn closure is satisfies this condition. This tells what? This tells Vn closure equal ux1 closure union xs are the components. So Vn un prime subset of Vn. This is x subset union of Vn. Okay. So that is the argument. Is this clear? Please let me know. Please let me know. Take your time. I shall be back in a few moments. Okay. So, is the argument clear to everybody? Please let me know. So, oh, okay. I hope this argument is clear to everybody. So, this is the first part. Now, for the second part, 1 minute. So, for the second part, so there is only if part. This tells that let x equal to union where each UN is open and UN closure compact. Okay. Clearly, this implies X is sigma compact. To see this that it is locally compact, given an given any x, any neighborhood v of x, take x belongs to UN for some n, then UN intersection v is the open neighborhood of x with the open neighborhood of x with mm, which closure which is compact. This implies UN intersection VN whole closure is compact. Hmm. So yeah, so that is the argument. So the argument, let me repeat, goes as follows. 1 minute, please. Okay. So X is equal to UN, where UN is an open and UN plus compact. So, so this tells that X is compact, okay, sigma compact. To see this, it is locally compact. So we choose any point X and any neighborhood V of X. Then by definition, we can consider UN containing X as an UN intersection V is the neighborhood of X with its closure is compact. So that tells UN closure, UN intersection V whole closure is compact. Okay. So that is the argument. Is this clear to you? Please let me know. Do take your time. Please let me know, is that clear to you or not? Okay. So I hope this argument is clear to you. Now we can go for the next thing, namely, so the next question is as follows. Prove that every locally compact, connected, oriented topological group. Sorry, it is not oriented, just compact connected topological group G is paracompact. Every locally compact connected topological group G is paracompact. So take your time, think about it. So I'm giving a hint also. Show that every locally compact connected topological group is sigma compact. Okay, take your time, think about it, let me know. I shall be back within a few minutes. Okay. So, hmm. So solution goes as follows. Okay. Hint is hint. Okay. Hint. There is nothing to hint. I'm gonna write a solution. There is no point of hint. So let U be an open symmetric neighborhood of G, whose closure is compact. Then consider the subgroup generated by U is given by union 1 to infinity un, and which is open, and being an open subgroup, it is also a closed subgroup, and hence G is equal to union 1 to infinity un, which is nothing but union 1 to infinity un closure. So this implies G is sigma compact and hence Lindelof. Okay, and Lindelof locally connected space is paracompact. So this is the full argument. So basically, 1 minute please. Basically, the argument was as follows: U so locally compact. So basically, we are choosing an U. So U be an open symmetric neighborhood regime whose closure is compact. The subgroup generated by U is given by union even closure, which is open. Being an open subgroup, it is also a closed subgroup. Okay. And hence G is equal to union UN. This implies G is sigma compact and hence Lindelof. So this tells Lindelof locally connected space is paracompact. So this is the argument. Please take your time. Let me know if you have any doubt or any confusion with this thing. Please take your time and let me know. Hmm. So, is this argument clear to everybody? Please let me know. Okay. So, I hope this argument is clear to everybody. So, that's all for the assignment 3. Now, let's go for the assignment 4. Okay. So, let me download the assignment 4. Hold on a moment, please. Hmm. Okay, so immediately you have the assignment 3 left also. So let's do the assignment 3 also. And hold a moment, please. Let me search it. Hmm. So, so assignment 4 is as nothing but as follows. So, okay. So now let's do assignment 4. Okay. Okay. If you have any question from the third assignment 3, please unmute it. So let me know. Else, let's start with assignment 4. Okay. Hmm. So first question, sorry, the first question is that show that sequentially compact T1 space is countably compact. So sequentially compact T1 space is countably compact. Okay. Hmm. So, okay, so basically, first try to recall the definition. What does sequential compact means? Sequence, uh, every sequence has a convergence of sequence. And countably compact means every countable set has a limit point. That is called countable compact. Okay. Now try to mm, on and also the same way every open cover has countable subcode. Okay. So try to use definitions and try to solve this problem by yourself. Okay, there is nothing to explain more till now. Okay, there is nothing to do actually. Indeed, please take your time. Let me know. In the meantime, let me search some other questions also. Okay, so okay, take your time. Let me know. So this question seems to be good in reality. Okay, okay. Hmm. Okay. So, the solution goes as follows. Since UN be countable open cover for X if it has no finite subcover, then choose Xn belongs to X minus union of UK, K is equal to 1 to N. Note that the set Xn n belongs to N is infinite. Since X is sequentially compact, the sequence Xn converges to in X to say X. Then X belongs to UN for some N. Since X is T1, it follows UN contains infinitely many elements of Xn. But we know none of xk with k greater than n are even, which is a contradiction. If x belongs to un for some n, and since x is t1, it follows that un contains a finitely many elements of xn, but we know that none of the elements xk, k greater than n are even, which is a contradiction, okay? So that is the thing, okay? Hmm. So X is so Basically, since UN may countable open cover for X, so if it has no finite subcover, then we can choose any xn belongs to X minus U. Note that the set xn is infinite. Since X is sequentially compact, the sequence xn covers in X, say X, and say X belongs to UN for some n, since X is T1 and follows an UN contains infinitely many elements, okay, of X. But we know that none of the elements X are k greater than R in UN, which is a contradiction, okay. So that is the argument, okay. I have this clear to you. Hmm. Okay. So yeah. So please take your time. Let me do any doubt and question, or else we can move for the next question. Okay. Okay. So please take your time. Let me know. I'll be back in a few moments. So, so I think this argument is clear to everybody. Now let's move for the next question. The question is that let, yep, X belongs to R be continuous, real valued function where X is countably compact. Then show that F is bounded and attains its extrema. Huh. So, so basically, it is countably compact. That is an open called countable subgroup. Now show that it is bounded and at its extreme. Okay. So basically, you have done the same thing with the compact. When this was compact, the same thing you have done, right? So try to replicate the proof here also. Okay. Wisely. Please take your time, think about it, let me know. The proof is such that for the compactness situation also that can replicate it. Here also you need to use a very nice trick in order to deal with the countability, but that's not a big deal, okay? Because the countability things comes into the real situations, okay? So basically the hint is replicate, sorry, replicate the proof for real situations. Sorry, I mean replicate the proof for compactness situation. Okay. Take your time, think about it, let me know. Mm, mm. Okay. So, so are you able to solve, Mr. Mustaq? If yes, please unmute yourself. Let me know. Mm. Okay. So that means that you are unable to solve it till now. 1 minute, please. So the solution. So now note that x is countably compact. So is f of x. Okay. To see this, if even be a countable open set countable open cover of fx, then if inverse un is a countable open cover of x. Now since x is countably compact, so we have a finite subcover if inverse un. Then this uni is a finite subcover of f of x. So that is the argument. Okay. So basically, what does this tells is that 1 minute. Hmm. So basically, since x is countably compact, so if x is so and it is quite obvious because image of complex comes the same way it can be. Okay. So if it is countable open cover. So since if you un is countable open cover of fx, you can consider f inverse un, which is a countable open cover for x. Okay. Now since x is countably compact, so we have a finite subcover f inverse un. So f inverse so that uni is a finite subcover for fx. So that is the argument. Okay. Is the argument clear to you? Please let me know. So the thing is, it is very easy. There is nothing complicated in this argument here at all. Please take your time, think about it, and let me know whether this thing is clear to you or not. Okay. Please let me know. Okay. And if you are able to understand, then please go for the next question. Anyway, by the way, I just noticed that it's a finite subgroup fx, okay? But the main problem has yet not solved. We have to show the boundary at its extremum, okay? How to do that? Since f of x subset of R is countably compact metric space, so it is compact. So it is compact as well. Okay. So the Heine-Borel theorem, if x is a closed and bounded subset of R, okay, this tells f is bounded and attains its extrema. Okay. So that is the argument. So yeah, so that is the full thing. Since fx of R is countably compact metric space, so it is compact as well. So now we can invoke Heine-Borel theorem and switch a closed bounded subset of R. Since it is closed bounded subset of R, it is compact, so it is nothing but third bracket A comp B form. So that is that if attains the extremas, okay. So that is the argument. I hope it's clear to everybody. Now, now let's go to the next question. So the next question is what? The next question is show that every metric space which is limit point compact is separable and hence second countable. In particular, conclude that every compact metric space is second countable. Okay. Take your time, think about it, let me know. Okay. So, sorry, what happened? Okay. So compact matrix is second countable. Okay. So that is the thing. So the argument goes as follows. Since X is limit point compact metric space, so X is compact, of course, and hence X is totally bounded. Now, so this tells for each n belongs to n, there exists a set Sn with x1, x2, xn, k, so that x equal to union b 1 by n xn I. We claim that the set x is equal to n belongs to n Sn. That set is dense in X. How to do that? So we are choosing X belongs to X and epsilon greater than 0. Choosing n belongs to n so that epsilon less than 1 by n. Okay. So that particular x and I with I belongs to 1, 2 can say that x belongs to b 1 by n x and I. That is dx comma x and I less than epsilon. Okay. Now, since every compact metric space is limit point compact, since every metric is a limit point compact, so the second part follows. So basically, what the argument was that, so X is compact. So basically, we are choosing X, the X can be written as union of B 1 by n x and I. And we claim that X is equal to union of n is a dense subset. Okay. Now, since n belongs to n, we are choosing epsilon, so epsilon less than 1 by n. Okay. Now, choosing x and I says that x belongs to b 1 by n x and I. That is d of x comma x and I less than epsilon. Now, since every compact metric linear compact, so it is second count. So the second part as follows. Okay. So that is the argument. So is that clear? So I hope so. I'm writing down the next question. Please think about it in your home. So let xi be sequentially compact spaces. Then show that x equal to product over xi is sequentially compact. Okay. Xi is sequentially compact and show that x equal to product over xi is sequentially compact. Okay. So how to do that? Or how to approach this problem? So, okay, please think about it in your home. So let's stop the discussion here for today. If you have It is HW basically. If you have any doubt or any question, please ask me in the next live session. Okay. So that's all for today. If you let me know if you have any doubt. Okay, if you have any doubt, so I am leaving the session. Thank you for your time. We shall meet on the next Friday, 7 to 9 p.m. In between, if you have any doubt or any question, please drop an email. I shall get back to you as soon as possible. Okay. Thank you. I will leave the session.